And today I'm going to talk about my work on copositive duality for discrete markets and games. And feel free to ask any questions if while I'm giving the talk or after the talk. And this is a work during my PhD, and it's a joint work with my PhD advisor, Burer, and also with Josh Taylor. Both of them are faculties at University of Toronto. And I just want to give a heads up that this is a kind of interdisciplinary work. So I have like about 15 minutes of introductory material at the beginning, including some literature review on energy market and optimization. And if you kind of feel bored about those like simple things, you can just feel free to check your email and do anything else. And you can just jump in after 15 minutes when I start to talk about cooperative programming. But if you are not very familiar with like energy market and pricing, then I think it might be a good introduction about this topic. Okay, so the starting point of my work is on is the economic equilibrium, and this is a concept about a balanced and a stable state in an economic problem. Some examples of economic equilibrium problems include a market equilibrium, which means we have supply equals demand in the problem, and also we have individual rationality, which means no one wants to deviate from the equilibrium point. And here is a picture to illustrate a market equilibrium in a like chocolate bars market. The equilibrium point is $1 and 15 chocolate bars. And at this point, no one wants to deviate from the equilibrium. And for those of you who are familiar with game theory, Nash equilibrium is another type of economic equilibrium where no player wants to deviate from the point given all other players' decisions fixed. Also in transportation networks, there is this concept called wardrobe equilibrium. It is basically a Nash equilibrium with each player being infinitesimal, and it is often used in traffic networks. So here are those are some examples of economic equilibrium, and and this concept is widely used in many economic problems. So if we luckily have a convex problem or a convex model for our problem, then the equilibrium point can commonly be obtained through strong duality. And for example, if we want to get an equilibrium price in a convex market problem, then we can just use the shadow price in the convex programs or convex optimization problems for those modeling. And if we have convex games, which means if each player is solving a convex optimization problem in the game theory problem, then there are like well-established theorems for the existence and uniqueness of Nash equilibrium. And also we can calculate the Nash equilibrium using Crash-Krohn-Tucker or KKT conditions. However, if we do have discrete decision variables in the problem, for example, in power system, you might have binary decisions in unit commitment problems, then we usually do not have strong duality in our problem because it is non-convex. And you might say that for mixed integer programs, we have Lagrangian dual, but it is definitely not a strong dual. And also there are like sub-additive dual or augmented Lagrangian dual for mixed integer programs. But the thing is, there is no like analytical form for those dualities. So it's hard to use them to get some like theoretical results. And what we do in this work is to start from a non-convex mixed integer program and convert it exactly to a copositive program, which is convex. And this transformation is from the literature, and it is exact. And then because we have a copositive program, we can use the strong duality of the copositive program, and it's like other good qualities, like good properties like KKT conditions. And we apply this kind of transformation relationship to applications like discrete pricing problems and discrete game problems. So for our discrete pricing problems, we apply this on electricity market with discrete decisions. And currently, the pricing schemes on those markets are unable to recover costs of generators, and our work tries to deal with this challenge. We also apply this relationship on games with discrete decisions, where in the literature for those games, there are like algorithms to find equilibrium for pure integer problems. However, in general, the theoretical results are lacking for discrete games, and we also try to deal with this challenge in this work. So our starting point is the pricing problems in non-convex energy markets. And why do we care about pricing in energy market? So we care about it because energy market models are really very widely used by both private companies and policymakers to make operating investment decisions or environmental and energy policies. And if we have a good market design, we should be able to efficiently match demand and supply, and there should be no oversupply or undersupply. However, the current pricing schemes are unable to recover the total costs of generators. So the generators might be operating under deficit. This creates the so-called missing money problem in power system. As a result, the generator owners might not have enough incentive to invest in new generators. So I also want to give you a crash course on how electricity prices are set in practice and in the literature. So in common practice, prices are usually given by the dual of the demand constraint in the unit commitment problem, and all the independent system operators or ISOs in the US are using some pricing method that's based on the concept of optimal shadow prices or the dual prices. And none of them are categorically wrong. However, the best way to determine the prices remains an open question. So for those of you who are not too familiar with duality, here is an example of how to get linear programming duality. And in our work, we are getting the duality for copositive programs. And the method is similar. You just get the dual problem from the Lagrangian dual, but the copositive programming duality will look a little bit more complicated than this one. And here is a simple example of the unit commitment problem where from which we derive the electricity prices. So in the unit commitment problem, we want to decide the operation schedule of generators at each hour. And here is an example of the result from a unit commitment problem, where in each hour we are deciding how much production we have using each type of generator, including coal, natural gas, solar, and wind. So in an abstract form, in the unit commitment problem, we are minimizing the total cost, and we have this demand constraint and also a bunch of other operational constraints. And we have both binary variables and continuous variables. So in an ideal world, if we had a linear program, then we could get the optimal shadow price or the market equilibrium price from the demand constraint here. However, because we have a binary variable here, we have a non-convex problem. So we don't have a duality. And someone might want to just relax those binary variables and get a LP linear programming relaxation and get the dual price. However, as I think many of you know that there is a duality gap usually between the mixed integer primal and the LP dual problem. So as a result, if we do use the LP dual, then we could underpay the generators, and again, we have the incentive problem. And we might have undersupply, which we don't want. To deal with this challenge, there are many works in the literature, and here I go over some of the works in the literature that tries to deal with this challenge of missing money problem. So the first one is the most famous one and most widely used in the US energy market. It's a restricted pricing scheme. So what they do is just they solve the mixed integer program as it is, and then they fix the binary variables. And in this way, you get a linear program. And then you can resolve the linear program and get the dual price. The problem with this pricing scheme is that the generators are not necessarily profitable. So we could still have the missing money problem, and we will need some subsidies to make up for that deficit, which could distort the market. And another pricing scheme is called convex Hull pricing, which can theoretically minimize the subsidies. So what this pricing scheme does is to just get the Lagrangian dual of the unique commitment problem. And theoretically, the duality gap for Lagrangian dual for mixed integer programming is smaller than the duality gap for the linear programming dual. So intuitively, the prices are the subgradients of the value function for the unique commitment problem. And because the Lagrangian dual could be hard to obtain sometimes, like numerically, so in real life, people could implement an approximation for the convex Hull pricing, which is used in MISO in the US. So they just basically do a linear relaxation of the unique commitment problem and get the dual price. And they need to make sure that the unique commitment formulation is very tight, meaning that the duality gap should be very small to make sure that the price makes sense. And finally, the last type of pricing scheme I want to mention from the literature is the Primal-dual pricing. This is a pricing scheme that explicitly seeks revenue adequacy for generators inside the optimization problem. Revenue adequacy means they want to make sure each generator is not losing money by operating in the market. So this pricing scheme first uses the primal constraints and then also getting the dual constraints. So here I say LP constraints because without the binary restriction, you just have a bunch of linear constraints in the unique commitment problem. So you get the linear program, you get the primal unique commitment constraint and dual unique commitment constraints, and you add back the restrictions about the binary variables. And then in the objective, they are minimizing the duality gap between a primal and dual. And this is kind of approximating market equilibrium because in market equilibrium, you have a zero duality gap. And finally, they have a revenue adequacy constraint that says for every generator, the profit should be greater or equal to 0. And this pricing scheme is kind of nice in theory, but it's really hard to implement in practice because it has a lot of constraints and it might have like nonlinear programming, I think mixed integer nonlinear programming form as an optimization problem. So it's not used in the practice right now. Okay, so that's all about the literature review of the energy market. And if you were distracted by something else, I hope to bring your attention back to the talk. And I'm going to talk about some things we do in this in our research. So our research uses copositive programming, and I want to first tell you a little bit more about what is a copositive programming. So copositive programs are based on the copositive conic constraints, and the copositive cone is defined as follows. So this looks as like the positive semi-definite or PSD cone definition, except that for the vector y, we have a non-negative valued y instead of real valued y. That's the difference between copositive cone and the PSD cone. The dual cone of copositive cone is called the completely positive cone. So copositive cone is not a self-dual. Its dual cone is a different cone, cone. And the completely positive cone is defined as follows. And this again looks like the Cholesky decomposition of the PSD cone, except that again, X is non-negative valued instead of real valued. And in the literature from the classical result by Parillo in his year 2000 thesis, it was proved that the copositive cone and the completely positive cone can be approximated, either inner or outer approximated by PSD cone and non-negative cone. So this result is widely used for approximately solved copositive programs, because SDPs are like easier to solve. Our work is relies on this very important result by Sam Burer in his 2009 paper, which says that any mixed binary quadratic program, MBQPs, can be reformulated as completely positive program. So a mixed binary quadratic program is basically a generalization of mixed integer program, and you could have quadratic terms in the objective. So any such problems can be reformulated as a completely positive program. And what is a completely positive program? It is basically a linear program over a completely positive conic constraint. So we have linear objective, linear constraints, and then we have a conic constraint like follows. And the dual of the completely positive program is a copositive program, and it's a linear optimization over a copositive conic constraint. So those two problems are usually solved by SDP approximations in the literature. So here is a picture to summarize the relationship among the concepts I just mentioned. From a non-convex mixed binary quadratic problem, we can do a reformulation, and the reformulation is a completely positive program, and its dual is a copositive program, and both of them can be approximately solved with SDP approximations. So let's take a closer look at this classical result by Sam Burer, which transforms a non-convex problem to a convex problem. So we start from a mixed binary quadratic problem, where we could have a quadratic term in the objective, and this quadratic term is not necessarily convex quadratic. We might have non-convex quadratic terms too. And then in the constraint, we might have binary variables. So the non-convexity could come from two parts. One is the quadratic term, one is the binary term. And this problem can be exactly reformulated to the completely program in the right. So the reformulation is basically taking the product of X and X transpose and lift it to the space of big X, the big X matrix. And then in this way, we transform the objective and the constraints to linear forms. And then we add this completely positive conic constraint into this convex problem. So basically, the NP hardness of the non-convex quadratic term and the binary term in the left are transformed into the NP hardness of the completely conic constraint in the right. And what do we?
Sorry, and these are equivalent form. It's not a relaxation just yet.
Yeah, they are exact reformulation of each other.
Fantastic.
So what do we mean by exact reformulation? Here's my next click. It means that the objectives of the two problems are equivalent. And also, if we have an optimal solution for the convex problem, then the small x in the optimal solution is inside the convex hull of the optimal solutions for a non-convex problem in the left. And this is important because this indicates that the small x from the right side isn't necessarily binary. If it's non-binary, it means it's in the convex hull of the binary variables from the left. And also, if the problem in the right-hand side has a unique optimal solution, then we can make sure that small x is binary. Otherwise, we might get a continuous solution for small x. And this difference is important, and we need to some more results to deal with this kind of challenge in our work. And I will talk about this later. Okay, and here is summary of what we do in our work. We start from a non-convex problem, and then we reformulate it to a convex, completely positive program, which has strong duality with copositive program. And we first apply this relationship to energy market problems and derive a pricing scheme based on this relationship. And then we apply this relationship to a game theory problems, which is also a non-convex game theory problem. And we get some novel existence and uniqueness theorems for pure strategy Nash equilibrium. And we also find a way to calculate Nash equilibrium using KKT conditions. And finally, we derive a cutting plan algorithm that solves copositive program exactly. And this is novel, and it's different from the SDP approximation, which is, after all, an approximation method, although it's widely used in the literature. And our contributions include proposing a notion of duality for discrete problems. And we also propose a novel copositive programming-based pricing scheme for non-convex energy markets, which is revenue neutral and individually rational under certain conditions. And we also provide a modified copositive programming-based pricing scheme that is free from the uplift costs. And also for the game theory side, we obtain some theoretical results for non-convex, again, a type of non-convex game called mixed binary quadratic game. And we get, as I said, existence, uniqueness conditions and KD conditions for pure strategy Nash equilibrium. And also we simplified the KD conditions, which contain some bilinear terms, into a single copositive program for special type of non-convex game. And finally, we propose an exact cutting plan algorithm for mixed integer copositive programs. And those are all our contributions in this work. So in our first application, we propose a pricing scheme for non-convex energy markets. And again, we start from this unit commitment problem, where we have continuous decision variables and binary decision variables. And then we convert this mixed integer program into a completely positive program using the result I just mentioned by Burer. And then the dual problem of this completely positive program is a copositive program. And it can be written as follows in an abstract form. And we use all the dual variables that appear in the objective in our pricing scheme. So lambda, big lambda, phi, and big phi are our electricity prices in our work. So more specifically, if we let those dual variables as our prices, then at our T, the system operator would collect the following payment from the demand side and pay the following payment to the generators. And because we have strong duality, we are able to prove that for system operators, the revenue from demand equals the payment to the generators, which means the system operator is revenue neutral, which is desirable. And we also proved that the total revenue for the generators equals the total cost of the generators. And so we have revenue neutrality for generators as well. And we can also prove that under certain conditions, we have individual rationality. And individual rationality plus the constraint that demand equals supply will provide us with a market equilibrium. But there are also some drawbacks of this pricing scheme. One is that the revenue neutrality may not hold for individual generators. It just holds for the aggregated level, the total revenue and total costs. And also, the prices contain some generator-dependent prices, fees. And in real life, we don't want our electricity price to depend on which generator it comes from. We just want to pay a uniform electricity price for different types of generators. And to deal with those challenges, we propose another pricing scheme, called revenue adequacy, copositive dual pricing. And this pricing scheme makes sure that for each generator, they are not losing money, their revenue is greater or equal to their costs. So we are able to do this because we have direct access to the pricing problem. Now we use a convex reformulation, while the other pricing schemes usually don't have direct access to the pricing problem. So it might be hard for them to do what we do here. So what we do is just to take the dual composite program, the dual pricing problem, and add a constraint that says that for each generator, the revenue should be greater or equal to the cost. And this ensures revenue adequacy for individual generators. Our second application is on mixed binary quadratic games. This is a type of non-convex game. And an example of mixed binary quadratic game is the Bimatrix game. For example, the famous prisoner's dilemma is a type of Bimatrix game where two prisoners need to decide whether to confess, and the optimal solution for them isn't the Nash equilibrium solution for them. Also, Kuno game in energy market is another type of mixed binary quadratic game where where we do have binary decisions in the game. So more specifically, in MBQ game, we have n players, and each player solves a mixed binary quadratic problem as follows. And the pure strategy Nash equilibrium X star for all the players would look like this. So this basically says that if all the other players' decisions are fixed at the optimal level, then player I should not want to deviate from its optimal decision. And again, the same trick, we reformulate the non-convex mixed binary quadratic problem to a convex completely positive program. And in this way, we reformulate a non-convex mixed binary quadratic game to a convex completely positive game. And we are able to prove that the Nash equilibrium of the non-convex game is equivalent to the Nash equilibrium of the convex game. And using this equivalence, we are able to prove some results for the non-convex game by extending some classical results from the convex game. So one classical result we use from the convex games is this result. I think anyone who have studied game theory should be familiar with this theorem, which says that if each player has a strategy set that's convex and compact, and if their payoff functions are continuous, and if the payoff function is concave in the maximization case and convex in the minimization case, then there should exist at least one pure strategy Nash equilibrium point. This is a result from like 1950s and a very classical result. And now because we have a convex problem, so we can extend this result for our case. So we extend this result that says that for a non-convex game, a pure strategy Nash equilibrium exists if all the three conditions hold. So the first condition is basically for the reformulation from the non-convex case to the convex case. It might look a little bit complicated, but actually it's not too hard to satisfy in our numerical experiments. And then the second condition basically says that I want the quadratic matrix QII to be a PSD, which is kind of an extension from the requirement that the payoff function to be convex or concave in the convex case. And then the third condition says that the completely positive game should have a pure strategy Nash equilibrium that satisfies the small x being binary. This is what I mentioned before, that the small x might not necessarily be binary, but if we do have a binary small x, then we can convert the convex solution to the non-convex solution, and we're good. So someone might raise the question, if you are familiar with the Bimatrix games, you might know that for some of the Bimatrix games, you might not have a pure stretch Nash equilibrium. And what it means for our theorem is that for all bimetric games, we can actually get a pure straight Nash equilibrium in our convex problem because it satisfies all the conditions here, but it might not satisfy the third condition of converting the convex solution to the non-convex solution. So in that case, the bimetric game might not have the Nash equilibrium. Otherwise, it should have the Nash equilibrium. And then we can also obtain a uniqueness condition for pure strategy Nash equilibrium, which says that if we satisfy all the conditions 1, 2, 3, and additionally, we satisfy the condition, oh, sorry, this should be 4 and 5. So if we additionally have those conditions, then the pure strategy Nash equilibrium for non-convex game should also be unique. So what it says is that first, we must have certain regularity conditions for our convex problem, such as lattice condition. This is like a very common assumption for many convex problems. But surprisingly, we didn't need this condition for the existence result. We only needed it for the uniqueness result. And then the last condition says that the payoff function should be diagonally strictly convex, which is again extended from the convex result. And also, we can compute the pure strategy Nash equilibrium using the KT conditions. So the KT conditions, as you can imagine, would contain bilinear term for the complementary stackness constraints, and then also have copositive conic and completely positive conic constraints. This will mean that the KT conditions are very, very hard to solve. But luckily, for a special type of mixed binary quadratic game, where if we have all the variables being binary and all the constraints are equalities, this looks like a little bit restrictive, but actually the bimetric games belong to this category. Then the KT conditions can actually be reformulated to a single mixed integer copositive program. So we don't have bilinear term, we don't have completely positive conic constraints, we only have copositive conic constraints. And this is a copositive program that we can solve with our cutting plan algorithm. So here's our cutting plan algorithm. We deal with this mixed integer copositive program where we have copositive conic constraint here. We might also have some integer variables here. So what we do is we relax this conic constraint and formulate our master problem or the relaxed problem. And to strengthen the relaxed problem, we add back some cutting plans. And the cutting plan is generated from this mixed integer program from the literature, which decide if a matrix omega is copositive or not. And if the objective of the separation problem is greater than 0, then the omega is not copositive, then we need to cut off this solution using the following cutting plan. And if the separation problem objective is 0, then we get an optimal solution and the algorithm can terminate. So a few comments on the algorithm. First, the algorithm is exact when it terminates, while the SDP approximation widely used in the literature is not exact, it's an approximation. And also, I think we are one of the few exact algorithms for copositive programs in the literature, and like one other copositive program algorithm that's exact that we know is this one by Boniface and Dual, which uses simplicial partition. But the problem here is that simplicial partition might be hard to implement, while our cutting plan algorithm is purely mixed integer programming based, and it's straightforward to implement using any mixed integer programming solvers like Groby and Cplex. And I actually prefer Cplex in this case because I think Cplex might have a smaller tolerance, so the cutting plan result is more accurate than Groby for my implementation. And also, our algorithm is applicable to mixed integer copositive programs, while I believe the other algorithm or the RCDP approximation cannot deal with mixed integer terms. in the conic program. So some improved ideas for the algorithm that I would like to implement in the future is that we might need a tighter master problem to start with, and also we might want to bound the master problem because at the initialization it can be unbounded. And then we also need stronger cuts to speed up the convergence because the convergence can be sometimes very slow. So we compared our cutting plan algorithm with the SDP approximation on a max click problem set. And we find that the cutting plan algorithm usually converges in a few iterations for this problem instance. This is generally not true for our problem instances, but this is true for this instance. We also find that sometimes our cutting plan algorithm can be faster than the SDP approximation, even though we are an exact algorithm and the SDP approximation is an approximation. We also compared our pricing scheme with other pricing schemes for energy market. And first, we find that the restricted pricing, which is the most widely used pricing scheme in practice, can be very, very volatile with the change of load. And this is a known observation from the literature. Many other literature also report this observation. And also restricted pricing will require generator-dependent prices, much like our first pricing scheme. And also we find that convex Hull pricing does not ensure revenue adequacy, so it does need some subsidies or uplift payments, as shown in the picture here. And as I mentioned, our first pricing scheme has generator-dependent payment. And I think it might be reasonable to assume that our first pricing scheme would also be very volatile, like the restricted pricing scheme, because after all, you would have some generator-dependent payment, like in the picture. But actually, we find that our first pricing scheme is much more like the convex Hull pricing. So the green line and the origin line for those two pricing schemes kind of coincide with each other for most of the time, which is kind of an interesting and surprising result for us too. And also our second pricing scheme, the revenue adequacy CDP pricing scheme, does not require any uplift payment as shown in the red dashed line here, which is desirable. We also did some experiment with Bimatrix schemes, and we find that all the instances converge pretty fast. And I want to mention that the state-of-the-art Bimatrix scheme algorithms can be faster. However, our method is more general and has the potential to be applied to other games. So it's not like really a specialized algorithm for Bimatrix schemes. Okay, as a summary, we proposed a notion of duality for discrete problems and a novel pricing scheme for non-convex market and some theoretical results for non-convex games. And finally, we proposed an exact cutting plan algorithm for mixed integer composite programs. And some of the future directions we want to try, or like anyone from the audience are also welcome to try this. And is that we want to apply this kind of reformulation relationship to other types of economic equilibrium problems, because many of the economic problems also have like discrete decisions, which might be hard for them without this technique. And we also want to simplify the completely positive reformulation, because currently this reformulation is kind of rigid. It does not allow inequality constraints, and it might also have some it has a lot of constraints, so it makes the solution of it very hard. It would be nice if we can derive some simplified version of this reformulation. And finally, we also want to improve the cutting plan algorithm. So the paper is available at Optimization Online and Archive. And thank you for your time, and let me know if you have any questions.